Okay, in this mini lecture, I'm going to explain to you how to find the inverse Laplace of a transfer function and its benefits. Okay, so what we have a transfer function with the step input. So if you multiply them out, it's going to be the step input 1 over s, which is the Laplace of a step input. Okay, that's your transfer function. And if you factorize it, you've got s plus 1, s plus 2. Because it can be factorized, you don't need to use quadratic equations. So this is very simple to solve. So you factorization, you've got the s, and then you factorize the brackets. It's s plus 1. If you multiply them out, you're going to get back to this equation here. Go to the next. We're going to apply partial fractions. So we're going to divide this into 3. You've got the step input, and then you've got the two results of the factorization. You've got a over s, b over s plus 1, and c over s plus 2. Divided into 3, we've called it a, b, and c. We need to find the values of a, b, and c, because what we have here, in technical terms, we actually have 3 graphs. We have the graph for the step input, we have b, and we have the graph for c. When they're added together in the system, okay, they actually produce one final graph, which is the response of the step input. Okay, so we have a standardized equation here, s plus alpha equals 0. So what we need to do is find the poles. Okay, so sa, the pole for the s, for the a part of the partial fraction, is s plus 0, because it has no real value after the s. It's going to be s plus 0 equals 0, so sa equals 0. So the pole here is 0. Sb, s plus 1 equals 0. So the pole for this, for here, is going to be s, is going to be sb, is going to be minus 1, and for sc, s plus 2 equals 0. So therefore the pole is going to be minus 2. Okay, so you've got 0, minus 1, minus 2. These are the 3 poles for these partial fractions here. Okay, and it's obvious, you can see minus 1, minus 2, and 0. You can just deduct it visually as well. Okay, now, so we're going to use something called the cover up rule, which is the best rule, I reckon, for solving partial fractions. And we're going to use cover up rule for a, b, and c. So let's do for a first of all. So the idea is this is the equation from this here, and you're going to cover up this part here. We know for a, the pole is 0, so we're going to replace the s's for zeros. So what you end up with here is basically, you're going to cover this up, so you're left with 1 over s plus 1 and 1 over s plus 2. So you're going to pretend that part doesn't exist here. Okay, it's from that basically we've covered up this part here, the s. Okay, now, so it's 0 plus 1 times 0 plus 2, it's 1 over 2, so a equals a half. This is simple mathematics. So we would replace the pole with 0, because the pole at a is 0, as we calculated earlier. We'll put zeros in places for s. We're just taking away this. Okay, now pole for b, sorry, for b I should say, pole is minus 1, because it's here, minus 1. So we're going to cover up b. So if you cover up b, you're going to cover up this part here. So what you're left with is s plus 2, s times s plus 2. Now the pole is minus 1 for b, so it's, and the answer is, for b is minus 1. Now for c, we're going to cover up c, so we're going to cover up c, which obviously means covering up, the actual equation itself here. So you're going to be s plus 1, s over s plus 1, because we've covered up c, and we know the pole is minus 2 for the c part of the equation, so it's going to be minus 2 times minus 2 plus 1 equals, which equals a half. So c equals a half. So a, b, and c we've solved. Put them back into the original equation. I've got to turn my mobile phone around. Okay, so you've got a, b, and c, 0.5, b is minus 1, and c is 0.5, as you can see here mathematically. Let's make it a bit more prettier. So you've got half s plus 2 minus s plus 1. I've just rearranged it just to make it a bit more, put the positives and negatives separate, you know. It just looks a lot better. Better this way. Okay. Now, and what do you do next? Next you I've got here s plus 1, I've got a half here, I've got s plus 1 here. So we're going to inverse Laplace the entire equation at the top. Okay, so let's inverse Laplace this. Just did a very tiny baby mistake. I forgot to put the 1 over s plus 2 and 1 over s plus 1 over here. Okay, it's very important you do that. Don't forget, you got your numerator and you got your denominator as well. Okay, so what all I've done is just taken this equation here, just taken things out, made it a bit more simpler. So it's half s plus half 1 over s plus 1 minus 1 over s plus 1. Okay, so now, so this is your A, this is your B, and this is your C here. Now this is your A, this is your B, and I've put the C here. I've just rearranged things. That's all I've done. Now, so put this into, take the inverse Laplace of this, half s plus half 1 over s plus 1 minus 1 over s plus 1. Now you're going to end up getting this 0.5. Take away the s. 1 over s, 1 over it's a half e minus 2 over t minus 2, okay, over times time, minus e over t, it's just 1t, so it's going to be et, okay, e to the power of e to the power of time. Now let's plot this. Try and do this. I'm going to hold the phone, and I'm not very good at doing this actually. So you've got, first of all, your constant, this step input, 0.5. That's this part here. Then the half. Now the bigger the multiplication by t, the longer the actual time delay. So you've got here starts off at a half, so which is there. So I'm going to exaggerate this probably just to make a point of it. Actually, it's very hard to do this. Okay. And then you got minus t. So you got your 3 graphs. You add them together. Any point. So you got. Sorry, I've run out of space to do the graph. So what I'm going to do, I'm just going to move over to this piece of paper here. I'm trying to show you together how you can deduce the graph. It's not obviously going to be exact, it's just a deduction, an estimation of what you expect the waveform to look like. So first of all, you got your constant 0.5. Okay, 0.5, that's your step input. Okay, then you've got your half times the exponential of minus 2t. Now, the bigger the factor, multiplication factor in front of t, the longer the decay. Because it's a minus t, it's going to be a decay. So what you've got here is, so you start off from here, half, and it's going to be a decay slow. I'm exaggerating, by the way, just to make a point. Now here, it's 1. It's not half this time, it's 1 times exponential times the power of t, so it's going to be here. It's going to be a bit quicker. So decay here is going to be a bit quicker. Hopefully you can see. So now you have your 3 graphs. Got your A, your B, and your C. Now to get the final graph, all you have to do is add them together. So you've got 1. Okay. You got 1. If you look at your graph, it's these two, and it's always subtracted by this one here. So it's going to be 0.5 constant plus 0.5. That's going to be 1. Take away 1. So at that point here, it's going to be 0. Okay, and what you're going to find is eventually it will rise. You will get a graph similar to this. In fact, I should say, in fact, that's wrong. It's actually not that. It's similar to this. The graphics, it won't go higher than 0.5. That's going to be the gain of the graph. Okay, so it's going to go here. Because when these two are 0, absolute 0, eventually, there's that 0.5 is always going to be here. So what's going to happen eventually, it's going to settle to 0.5. That's probably the worst graph you've ever seen in your entire life. Okay, if I just draw a very quick version of it here. I'm just finding it hard because this is 0.5. This is one graph. This is the other graph. And then the output will be final. There. Okay, that's what it should look like. Get the final output. That's just so that you don't actually normally have to do this in assignments, but just in case you do have to show the results and output, that's what it should be. So you've got your here is your, that's your A, that's your B, and that's your C in this case. Okay, and you add them together, that's what you should get. Okay, thank you.